All right, this is the last set of videos for the course, and we're going to start off by switching gears. For the bulk of the course, we've been talking about abstract data types and data structures to implement them. Now we're going to talk about one very specific data processing operation, one of the ones that's probably one of the most fundamental in computer science, and that is sorting, putting things into order. Just like we saw, lots of data structures can represent the same abstract data type. Lots of operations can be used to implement a sort. Now, you've done sorting already here in 108. You probably saw bubble sort, selection sort, insertion sort, and these are all iterative, meaning that the way that you'd sort is you go through the list, iterating through each element and figuring out some way to order it. You also probably talked about how the running time of these was quadratic in the size of the list. In other words, the sort is big O of n squared. And why is this the case? Well, think about it for a second. Each of these sorting operations has a bunch of loops, and each loop iterates between 1 to n times. So let's suppose that you're doing, I guess you can pick any of these, and it kind of doesn't make a difference. But for each element in the list, you need to then go through each other element in the list. So to figure out where, say, the first number goes, you have to compare it to every other number and then put it in that spot. To figure out where the second number goes, you have to compare it to every other number and so on and so forth, right? And so this is why you get, if you want to combine them, at the very end of it, you only have two numbers to compare, so there's only one comparison at the very end of it. When you only have three numbers left, you have to compare the first one to the last two, so that's two comparisons. And if you keep going backwards, three comparisons, and the very first number you start with has to be compared with everything else, which is n comparisons. So 1 plus 2 plus 3 ... up to n is a summation you hopefully are familiar with, maybe, which is n times n plus 1 over 2. And the dominating term here is the n squared. We don't care too much about the rest of it. In this lecture, we're going to use recursion to go faster, making two faster sorting algorithms, merge sort and quick sort. These are recursive, and they are divide and conquer algorithms, which is a type of algorithm that has the following steps. First, take the input and split it up into smaller parts. This already should sound familiar to you. For each of these smaller parts, recurse on that part separately. And then once you have results, combine them into a single result. Now, while quicksort and merge sort differ on how they split and combine, merge sort does the quote-unquote hard step when it's combining things together, and quicksort does the quote-unquote hard things in the dividing step, and we'll see how these two differ from one another. So the first algorithm we're going to look at is merge sort, and this uses a quote-unquote divide and conquer philosophy very literally. So the idea is you take the list, you split it into two halves, and you sort that half recursively using the merge sort algorithm. Once you have your halves sorted, you merge them together into the final sorted list. And here's what our little algorithm looks like. Merge sort takes a list. If the list has fewer than two numbers in it, this is pretty straightforward. That means it's either just one number or it's empty. That means it's sorted. We're already done. Okay, what if it's not? Well, we figure out what the midpoint is of the list so that we can split it in half. We take the first half and the second half and we merge sort them using our merge sort algorithm. So here's the left half, here's the right half. And finally, once these two are sorted, assuming they are sorted correctly, we return the merged version of these halves. So this code seems really short, probably way shorter than you expected, right? That's because most of the complexity lies in this helper function here, merge, and that needs to take two lists and combine them into one sorted list. Now, for arbitrary lists that can contain any elements in them in any order, there isn't really an efficient way to combine them. For example, the first element of the return list should be the minimum in either one, and the only way to figure this out would be to iterate through both lists to find where that is. But if you know both lists are already sorted, this makes a huge difference. For example, if you want to find the smallest thing in either list, you only need to compare the first element of each of the two of them. Since they're already in order, the smallest element must be the first one of those two lists that's there. We can generalize this idea and say that for every comparison we make, we can add a new element to our sorted list. And this is why merge sort is so efficient. And of course, what gives merge sort its name? When you merge the lists together, you can immediately add something to your final return value that you're going to put in. So here is the algorithm for merge. It takes two lists, returning a sorted list with the elements in the two of them combined. And the very important precondition, the only reason this works, is that we assume both list 1 and list 2 are already sorted for us. This makes the world of difference. So we got two indices to go through our lists, and we're going to merge them together into a list called merged. Until we reach the end of one of the lists, we're going to keep going doing the following. Compare the first element of each list that we're at right now to the other list and see which one is smaller. So whichever one is smaller, that's the one that we want to add to our merged list. So we append that value and we increase our index so that we can skip through there, and we've already added it, that element, we don't need to add it again. And we keep doing this until we've reached the end. Now, at this point, either we have reached the end of the first list or we've reached the end of the second list. It could be either or, it depends. Sometimes one of them will be sorted in such a way that you reach that one first, and whichever way that this happens, the remaining elements of the other list need to be added to the end of your merged list. Now, only one of these two lists can have this happen, right? If you've reached the end of the first list, that means there's nothing left there to add. If you reach the end of the second list, there's nothing left there to add. So one of the two of them you don't need to add anymore. But to keep the code simple, we can actually write everything like this. Take our merge list that we've built from combining all of the compared values in order, add whatever is left of list 1, which could be nothing. Maybe that's the list we got through first. And add whatever's left of the second list, which again could be nothing. And presumably if we reach the spot, one of the two of these is nothing, but the other one does have stuff, and we need to make sure that that gets added. We could do an if statement, if index 1 is the one that's reached the end, then add the other, otherwise do the reverse. But just to keep it really clean, we can just add everything together and know that for this to work, one of these was empty. It could be either one. Now let's try it out, right? This is my philosophy for everything in this course is if you're not sure what's gonna happen with some code, run the code and observe, right? Okay, so here's our code. These should be lists with a lowercase because I'm using old version of Python. And we're going to take merge sort, and we're gonna just straight up run merge sort on a list. Let's run it with a list of 5 numbers of just randomness. So we got merge sort. Is that how they wrote it? Nope, no underscore. Of a list of number, and let's see what happens. It breaks immediately because I forgot to fix the list up here with a lowercase l because my version of Python is old. But if you're using PyCharm like you're supposed to be, this shouldn't be a problem. Okay, 115 steps, quite a bit, so we got some stuff to take a look at. But, let's work our way through. Okay, merge sort and merge are done. Let's run our merge sort. Great. Here is our list, 8, 3, 6, 4, 1. This is obviously in the wrong order. Our goal here is to get to the end result of 1, 3, 4, 6, 8. And once we've done that, we've sorted things correctly. Okay, now, base case. Have we shrunk our list down until it only has 1 or fewer elements? No, we have not, so we're not done yet. We need to do some recursion. We figure out the midpoint of this list. We can see pretty clearly here it should be a 2. How do we calculate that? Well, we take the length of the list, which has 5 things in it, and divide by 2. Note here, importantly, we're using integer division because we want to get from 5 to 2. 2.5 is useless to us because there's no elements are at index 2.5, which is why we do the integer division. Okay, we got our midpoint of 2. We're going to sort the left half using merge sort, and then we'll sort the right half using merge sort. But first, let's sort that left half. All right, so here is the left half of our original list, 8 and 3. No base case yet. We still got 2 elements here. So the midpoint here, we got 2 elements. 2 divided by 2 is 1. So we say our midpoint is 1. Obviously, it's not exact here, but got to split it somehow. So now we're going to sort the left and the right. So the left here is just an 8. Hooray, an 8 is sorted. Okay, great. We don't really need to do anything there. But now we know the 8 is sorted. We know the 3 is going to be sorted too. Kind of a trivial thing to conclude. And now we get to where the sort of chunk of the work actually gets done. Now here it's pretty simple. We only got 2 elements to work with, so merging them should be pretty easy. List 1 is the 8, list 2 is the 3. Our indices start at 0 and we'll never really go elsewhere. Our merge list right now is empty. All right, we're going to loop through till we've gone through all of our elements. So let's compare 8 and 3. Which one comes first? I think you can see the 3 should come first. So we append that to our list. Yep, there's our 3. We increase our index for the second list to 1. And now we don't need to go through anymore because we've completed going through this list that just had the 3 in it. So what's left here, we take our merged list and we combine everything that remains. In this case, all it remains is an 8. So we tack that on, and that's what we're returning. Okay, cool. So we are returning 3 and 8. That's the left side of our original list sorted. Cool. Now let's sort the right half. 6, 4, and 1. All right. No base case yet. Midpoint is 1, pretty clearly. We got to sort the left half. So if we're setting 1 to be the midpoint and we got to cut 3 elements in half, it's not going to be even. So we'll cut this in half and say, okay, well, 6 will be the left and the right will be 4 and 1. All right, so we got to sort 4 and 1. It's going to work the exact same way we did with the 8 and 3, right? We chop it up. So we got 4, which is sorted. We got 1, which is sorted. And we're going to merge our 4 and 1 together. I think you can probably do the math at this point. We're going to make the 1 go first, the 4 go second. And hooray, we got 1 and 4. Great. Okay, so back up here, we're doing our merge sort of the list 6, 4, 1, trying to put this in order. The left side we have a 6, the right side we have 1 and 4, and now we need to merge these together. Well, what do we do here? We compare the 6 and the 1. One of the two of these is the smallest thing that we have to work with. And it is, unsurprisingly, the 1, so we add that in. Okay, we've added the 1. Now we have to compare 6 and 4. Which one is smaller? 4 is smaller. So we continue to add that, and we keep increasing this index to show we're going through list number 2 with the 1 and the 4 there. All right, we've reached the end of that list. There are no more elements in this list to add, so what's left? We just add the 6. 1, 4, 6. Great. Okay, so from where we started, just calling merge sort on our list of 8, 3, 6, 4, 1. These numbers all over the place. Now you can see combining the last 2 lists is going to save us a little bit of time in the quote-unquote long run, right? Like if you can imagine these lists were 1,000,000 times longer, which would you rather sort? Something where the numbers are kind of all over the place, or here, these 2 lists are sorted, which means I don't need to compare all 5 of these numbers to figure out which is the smallest anymore. I just need to compare 1 and 3. And one of those, when I do my merge now, is the smallest number of the whole list that we have over in the top here. So, okay, we're going to go through these 2 lists, 3, 8, and 1, 4, 6. All right, merging them together, what's the smallest thing we have first? 3 versus 1, 1 is smaller, so we're going to go with that. We increment this index to show we're going through list number 2. We've crossed out our 1, now we have 4 and 6 left, 3 and 8 on the other side. And now we compare 3 and 4. 3 is smaller this time, so we're going to run this line of code, add the 3 in, and increment the other index. So now we've crossed off the 1, crossed off the 3, and we're on to the next part. All right, 4 and 8. Well, pretty clearly 4 is smaller, so we're going to add that one. Increase this index. Now we got 6 and 8. 6 is smaller. And now we've completed this whole list, so we don't need to do any more. We know everything that's left here must be bigger. So we tack on the 8, and look at that. That's what we wanted. All done. Now let's take a look at quicksort. So while quicksort also uses divide and conquer, it has a different philosophy for dividing up the input list. So here's one way to think about it. Suppose that you're sorting people alphabetically by their last name. And now one way you can do this is you divide people into two groups. One where their surname is A to L, and one where their surname is M to Z. This is kind of like an approximate amount because it's probably not the case that these will be exactly equal in size. But, it is an attempt to at least split them, and you do know that once you have done this division, everybody in the A to L group should come earlier than everybody in the M to Z group. Now you've split this in half, and so after you sort those groups, you basically are done. You take the two groups and you combine them to create a fully sorted list. So quicksort formally uses this idea. You pick some element, and we call it the pivot. This is sort of our midpoint that we're going to compare everything else to. We then split up the list into two parts. Everything less than the pivot, or equal, and everything bigger than the pivot. This is what you could call the partitioning step, where we're splitting things up. Now that we've done this, we have two halves. We sort them recursively. Unlike merge sort at the end here, the quote-unquote merging part is much easier because you know everything on one side is always going to come before everything on the other side. The merging is super trivial. You just put them right back to back. So here is our quicksort algorithm, returning a sorted list with the same elements as our list. This is non-mutating. It does not mutate the input lists. We're going to return a new one. So base case, there's only one element, or 0, it's sorted. Otherwise, okay, we pick a pivot. In this case, we'll keep it easy. We'll pick the first element. However, it could be anything. You could decide pick something in the middle, could pick one at random. It's up to you. Once you have your pivot, you partition the rest of the list into two halves where everything is going to be either smaller or bigger than our pivot. And we're going to use a partition helper function for this. For all of the smaller things, we're going to run quicksort on that and give us a smaller sorted list. For everything bigger, we're going to run quicksort on that to give us a bigger sorted list. And then we have a real simple combination here. We take everything smaller, then add the pivot, then everything bigger. And it should be in order already. No extra work needs to be done here. And it turns out that implementing partition is simpler than the merge helper. You can just do this with a loop. So here's our partition helper. Given a list and the pivot, we're going to create two lists. So a tuple of list 1 and list 2, where the first one is the smaller things and the second one is the bigger things. So smaller is going to start with nothing, bigger is going to start with nothing. For each item in our list, we compare it to the pivot. If it's smaller or equal, it goes in the smaller list. If it's bigger or equal, it goes in the bigger list. Okay, that's it. So let's give this a shot. Okay, so grab our partition. For the sake of, comparisons, we'll use the same list. I don't see why not. Lists and the term any cause weird issues with my old version of Python, so don't mind my corrections here. In PyCharm, you should be able to leave this exactly as is. Okay, yeah, cool. And we're gonna run quicksort instead of merge sort. Alright, what did I break? Oh, I forgot the lists. Needs to be lowercase. Okay, let's try that again. Now what did I break? Tuples also lowercase. Come on. Types of okay, fine. We're gonna leave all the type stuff out because it's annoying and it causes weird issues with my old Python stuff. Okay, cool. One thing we'll randomly note here, which I think I will comment on a little bit in the last video to follow this one basically, is that if you just look at this, and this is a really anecdotal piece of evidence, number of steps that it takes to do this, I believe merge sort was slightly over 100, down to 85 to sort the exact same list with a slightly different algorithm. So bear in mind that although both of these are divide and conquer recursive sorting algorithms, there are differences between the two of them. Now, how's it go? All right, quick sort and partition are the two functions we have to work with, and we're sorting our same old list from before, 8, 3, 6, 4, 1, and our hope is that we get 1, 3, 4, 6, 8 at the end. How are we going to do this? All right. So we are going to, first off, see there's too many things here to use our base case, so we got to move forward. All right, we're unfortunately choosing a poor choice of pivot to start off with. 8 is not a great number to compare because we're going to see everything is actually smaller than 8. So when we do our smaller, bigger partitioning, not a lot of good work gets done, but it'll hopefully improve in the subsequent call. So, all right. We're going to do our partition here. So we're taking the list of the remaining numbers and the number 8, and we're going to compare everything. So what's smaller and what's bigger starts out as nothing for each thing in our list. Starting with the 3, we compare. Well, 3 is smaller than 8, so it goes into our smaller list. 6 is also smaller. 4 is also smaller. 1 is also smaller. Everything goes in the smaller list. This was not actually a great list to sort with this quicksort algorithm, but you know, it'll get better. Okay. So what are we returning? Our smaller list is 3, 6, 4, 1. Our bigger list is nothing because nothing was bigger than 8. Okay. Our smaller sorted list is 3, 6, 4, 1. Now we're recursively going to sort this one. No base case yet, still too big. This time our pivot's going to be much better. We're going to choose a 3 here. So let's split up the list based on 3 as our next pivot. So smaller and bigger are lists that we need to set up. So 3 versus 6, 6 is bigger. 3 versus 4, 4 is bigger. 3 versus 1, 1 is smaller. Okay, cool. This is kind of more what we were hoping would happen. So now we have the smaller list is 1 and the bigger list is 6 and 4. So when we go back, smaller is 1, bigger is 6 and 4. Let's quick sort this one. Well, 1 is sorted, so it is done. We don't need to call our quick sort anymore on that one. It just returns itself. All right, let's do quick sort on this one, 6 and 4. This is not small enough that we can just say it's done. There is work that needs to be done. The pivot here is going to be 6. And when we compare the rest of our list, well, our list only has one thing to compare, and it's going to be smaller. So smaller is going to be the 4, and that's it. Okay, now we start actually doing some merging here. You can kind of see that we've like split up everything. We got our 4, our 1, our 6, our 3, and our 8 are all stored in separate places right now in our program. But we finally have managed to do a, or at least we're almost there. We're almost to the point where we can start merging stuff together. Okay, so 4 is sorted. It's all good to go. Okay, cool. So we don't need to worry about that. For our bigger list, we have nothing to do there. So now we're at the point where 6 was our pivot, and 4 needs to be combined with it in the right way. Well, we know 4 is smaller than 6, so the combination we're going to go with is the smaller sorted list of 4, then the pivot, which is 6, then the bigger sorted list, which is empty. So our return value ultimately is 4, then 6. Okay, in our previous recursive call, we want to take the smaller sorted list of 1, the pivot of 3, and the bigger sorted list of 4 and 6. And now you can start to see it's actually going in order, right? So there is our return value. Oh, we're almost done already, right? The merging here was real fast. Once we actually have everything kind of split up in the right ways, merging it just goes real quickly. All right, 1, 3, 4, 6. That's our smaller list. Our bigger list is already sorted because it's empty. And now when we combine things, we got our 1, 3, 4, 6, and our pivot of 8 goes at the end, so our return value is, hooray, the correct answer, exactly what we wanted.